Hi, all. Welcome back to another round of astronomy, and yeah, let's get at it. Last week. Cool. So, what you see in front of you is the original Hubble Deep Field to the right hand side. And to the left hand side, I have an interesting graph that I'll walk you through. On the bottom of the chart, down here, is, as you notice, the cosmic redshift. What the authors of this paper have done is looked at the Hubble Deep Field and measured the redshift for each of the galaxies in the Hubble Deep Field. So that's what they have plotted on the horizontal axis. Since redshift is related to how fast the galaxy is moving away from us, and Hubble's law tells us how to relate the recessional speed to distances, the redshift here could also be thought of as distance from Earth. If you prefer as well, you could say distance from Earth or distance in the past, right? Because the further away you are, the more in the past we are seeing you. So there's a couple different ways to think about that horizontal axis. The vertical axis is simply the number of galaxies displaying a given redshift. This kind of graph is called a histogram when you plot the number of objects versus a particular feature. So, what we have here are galaxies with given redshifts. And I'll ask you a question. What looks kind of goofy about this graph, this plot that I have here on the left-hand side? Yeah, you see it? Something goofy here. I'll highlight it for you. It's right there. Did you notice those? Those aren't artifacts. Those are gaps. It seems kind of odd that about distances corresponding to 1.6 to 2.3 in redshift, or about 3.5 to 4, those distances don't have any galaxies. Huh. So, universal structure. Now, how do we actually model what the universe looks like? Okay. So remember, we have some observations that inform the model that we build. So one of the observations is the cosmic microwave background. In other words, we have an idea about the temperature fluctuations in the early universe. That is our starting point. Assuming this order of fluctuations throughout the entire universe, then we can take that and fast forward in time. What else do we have? Well, we have an idea about gravity. We have Einstein's theory of general relativity from 1915. We have a good idea about how gravity can affect light and how gravity forms stars, black holes, galaxies, etc., etc. In addition to that, we also have an idea about the gravitational effects due to dark matter. Now, we don't know what dark matter is, okay, but we at least have an idea about how it influences galaxy formations, rotation curves, etc. So, taking the initial condition, the cosmic microwave background, which tells us how material is distributed in the early universe, and understanding the gravitational effects that material has on clumping together, we can now use our computer simulations, our model, and fast forward through time to see what the end result should look like for today. And if we start from the early universe and we fast forward through time, we see that given the fluctuations of material, those small differences in the early universe cause clumping of galaxies, right? Clumping of galaxies and places where there are not very many galaxies. Well, that's a prediction now, right? That is a prediction of our computer model about what the current universe should look like. Now we go out, we make our observations, and we can make predictions based on this. For example, you could say, on average, how large are the what we call voids, the places in the universe that lack any galaxies? How large, physically speaking, should those voids be on average? That's a prediction that we can make. Do we see strings of galaxies connected together? These are sometimes called walls, W-A-L-L-S. So we have voids and we have walls. And the question is, do we see this sort of structure today? How good is our prediction? Well, we have two survey techniques, or two surveys, that we can use to answer this question. One of them, the Hubble Deep Field, which we started this lecture out with. You notice that there were places where we saw galaxies clumped together, and then there are regions where we didn't see very many galaxies clumped together. Those would be the voids. A larger effort for this is called the Sloan Digital Sky Survey. And I'll give you, after a series of slides here, I will show you the results of the Sloan Digital Sky Survey. And that is an ongoing research. You ready for it? And you've probably seen something like this. So I'll start off with measuring distances to our local neighbors. So if we were back in the, 1920s, this is the entire universe. We have managed to get an idea that the Milky Way exists and there are other entities outside the Milky Way. For example, I say 1920s because it wasn't until 1923, 4, somewhere in there, that we were able to measure the distance to the Andromeda Galaxy, our nearest neighbor. To give you an idea, this is about 2.5 million light years. So this entire cylinder probably has a radius of, let's say, 5, maybe 7.5 light years. 7.5 million light years. Okay. Pretty cool. But we have to go further out. So we're using, for example, Cepheid variables to measure these distances. We have to go further out. And so we can start now seeing that wall kind of shape. This is what's called the Virgo supercluster, of which the local group, which is centered, is a small part of that. And again, you're now seeing regions, strips, where there are a lot of galaxies represented by individual points of light, and places where there doesn't seem to be a very high density of galaxies. So we can keep going further out. And as we zoom out, we still see these walls and voids. The Virgo supercluster is part of a larger group called the local superclusters. I know, astronomers are really creative. But again, now you're seeing not only these walls and voids at the microscopic level of the Virgo supercluster, but we're starting to see it at a larger, a macroscopic level. In fact, to the point where we have Boots void, Copernicus void, Sculptor void. We're starting to actually label the voids as well. And again, you can kind of see some of these structures, these filaments or walls as they kind of string through our galaxy. So here's a cool video from Nature, released I think 3 or 4 years ago, that said, hey, we can actually figure out where the boundaries of some of these walls are. For example, when I take a galaxy right here, say right there, is it part of the Centaurus supercluster or the Virgo supercluster? How do I actually find that distinction between those two groups from a gravitational standpoint? So I'll show you the results of the Sloan Digital Sky Survey. And again, let me walk you through this. You first of all notice that we are looking at particular patches, regions of the night sky. So around the perimeter of the circle, you'll notice the hours. What those are referring to are right ascension. So I believe the reason why you have only a particular pie slice of right ascension would be the night sky that's visible during a particular time of the year. And I believe also that the telescope that they use, I'd have to double check, but I don't think that you can actually move it. So you're only looking at one direction, one kind of range of the night sky for a given part of the year. And then the reason why you have this opposite pie slice is because 6 months later, the sun is in this region of the sky, and so you can look away from the sun to get the other part. So that's that. The center represents a distance of 0. And as you move radially outward, you increase in distance. So you increase in redshift. And again, just notice that there are regions where there aren't very many galaxies. And then we have regions that are highly dense, right? Walls again. I don't know about you, but I think that they kind of looks like a sponge. Like the overall structure, galaxies seem to clump together in these ridge portions, and then there's places where they don't clump at all, these voids. So we have at least several observations that would confirm this structure of the universe. Remember, our computer model says, hey, these galaxies should clump together into these regions of high density and low density. And indeed, that is what we are seeing in the universe. Okay. Hey, thanks for your attention. We're getting up on the end of the chapter, end of the semester. I'm hoping that we'll break into some black hole stuff and end with a bang. Thanks for your attention. I'll see you next time.